This lesson is going through graphing functions. Some functions really need technology to help see what they look like. So if we consider this function y equals 2 to the x over x minus 1, this clearly is not a standard graph that we're used to drawing. So we really need to use technology to help do the following. Find the axes-intercepts, find any turning points of the function, find any asymptotes of the function, and state the domain and range of the function, and sketch the function showing its key features. But before we get to the technology, let's think about what we actually can do ourselves. In A, we need to work out what the axes-intercepts are, so the x-intercept and the y-intercept. So for instance, for the x-intercept, this is when y equals 0. So this is when 2 to the x on x minus 1 equals 0. Now, that's a little bit hard for me to be able to do without technology, so we're going to do that with technology. Now, let's have a think about the y-intercept. This is when x equals 0, so therefore y equals 2 to the 0 over 0 minus 1. Now, this is undefined. So that tells me there's no y-intercept. So now let's look at technology and see if we're correct with the y-intercept. So I've opened a new graphs page and we're going to type in our function. So first I need a fraction, so I could control divide. So 2 to the power of x over x minus 1. Enter. Okay, so that's an interesting function. Now I think we can see, I might zoom out a little bit, but I think we can see that the y-axis is an asymptote because we approach the y-axis down here and up here, but we never quite hit it. So we were right in thinking there's no y-intercept, but there is an asymptote at x equals 0, or in other words, the y-axis. And also, by looking at the graph, we can see that it never crosses the x-axis. So there's actually no x-intercept either. So that's interesting. Now, question B says to find any turning points. So any maximum or minimum. Now, we can do this by pressing Menu, Analyze Graph. Now, I'm going to pick minimum because I think I see a minimum in this region here. So I'm going to choose a lower bound around here. Then move right to get to an upper bound, and there's my minimum point. So at 1.44 and 0.884, we have a minimum. Now over here, I don't think we have a maximum because it looks to me like we're approaching the x-axis. Another way you can check is by looking at a table of values. So Menu, Table, Split Screen Table. So I want to analyze what happens as x approaches negative infinity, so as it goes to the left. So I'm going to click on up and move, see what this table is doing. This column here are the x values. So I'm going where x is negative, and I'm continuing to go up. So in other words, I'm approaching negative infinity. So if I keep going, what is this? It looks like I'm approaching negative 1, I should say. Well, now we know it definitely doesn't cross the x-axis, but we also know we've got a horizontal asymptote at negative 1. Now to delete this table, I'm going to click on the edge like that so that it flashes blue, and I'm going to press delete, and now it goes away. So far we can graph our minimum point at 1.44 and 0.884, so that's about here. And I should probably put in brackets the coordinates 1.44 and 0.884. As usual, we try to do 3 significant figures and up. What do we also know? We've also discussed that there's a vertical asymptote at x equals 0 because we approach the y-axis but never touch it. So I'm going to draw that here. basically we already saw that as x approaches negative infinity, so as we're moving in that direction, the graph seems to be approaching -1. So because of that, we're actually got a horizontal asymptote at y equals -1. So our domain is all x not equal to 1, not equal to 0, because remember that's where our vertical asymptote is. So as we can see, for the domain, x can be anything. We cover all these negative values of x and we cover all the positive values of x, but x cannot be 0 because that's where there's a vertical asymptote. So for the domain, we have all real x not equal to 0. Now for the range, here's the thing. Basically, if I were to graph another function, we press tab, and I want to graph the line y equals -1. And that's that red line there. That's our horizontal asymptote. We never pass that. So as I said, that's a horizontal asymptote. So this part of the function down here never passes that line. So what does that mean? We do not cover the y values between -1 and including -1 because that's with a horizontal asymptote, and up to this point here, 0.884. So if I zoom in a little bit, it might help. So basically, the y values between this -1 where the horizontal asymptote is and the other y values below the minimum point here, these values in here aren't covered by our graph. Therefore, they're not included in the range. And our range is y that's bigger or equal to 0.884 and where y is less than -1. And now that we've found all those things, we can sketch the function showing its key features. So by looking at your technology version that I've shown previously, the shape of the function is something like this, but then it goes up quite steeply. So that's the top bit. And then the bottom approaches this horizontal asymptote and then stays pretty steep until it then goes downwards and approaches this vertical asymptote. So that's the function. And as you can see, that's why the range, so if you look closely, the range only covers from 0.884, or the y values only cover from here and up, and then from underneath this asymptote and down. And that's why the range is this here. Y is bigger or equal to 0.884, and y is less than -1. So now we've done all our parts of the function. Lastly, I should label it. Okay, so now you can see how we use technology and our own graphing skills to graph the function. And when you have to graph a function, girls, remember you have to graph and label the asymptotes. You can't leave that out. And just keep in mind that blue bit for where I was explaining the range doesn't need to be there in your sketch. Okay, now there's an important thing I want you to note. If you are asked to sketch a function, it should show the graph's general shape and its key features. If we're asked to draw a function, it should be done more carefully and to scale. So all the scale needs to work. Some important points need to be plotted, that kind of thing. So if I were you, just in general, try and take care with your sketches, do it to a scale, and make sure you put all important points. Okay, next question is, find where graphs meet. So suppose we graph two functions, fx and gx, on the same set of axes. The x-coordinates of points where the graphs meet are the solutions to the equations gx equals fx. So basically, when does gx equal fx? It's when their graphs intersect. And it's the x values for which the graphs intersect. Because if you look at this here, I don't see y anywhere in that equation. The equation is in terms of x. So therefore, the solutions to that equation are the x values of the points of intersection. So anyway, question 1, let's draw the function y equals 1 on x and y equals 2 minus x on the same set of axes with the domain -4 to 4. Now, it's not okay here just to show the basic shape. You need to be pretty accurate with your points as well. So for y equals 1 on x, just think about it. What's 1 on 1? Well, that's just 1, so that must be a point. 1 on 2 is a half. 1 on 3 is a third, so that's even lower, and so forth. Actually, that's probably a bit higher. And then 1 on a quarter is even lower. Then, going the other way, what's 1 on a half? That's actually 2, and so forth. So basically, 1 on x should look something like this. It's not okay to just do a basic sketch if we're going to use this to find points of intersection. Okay, now what's 1 on -1? -1. What's 1 on -2? It's -1/2. Then you got -1/3, then -1/4, and then 1 on -1/2 would be -2. So, oops, there's my function. Okay, so that's y equals 1 on x. The other one is y equals 2 minus x. So, y equals 2 minus 0 is 2. Y equals 2 minus 1 is 1. Y equals 2 minus 2 is 0. Oh, look at that. It's a straight line going through those points. Of course, we knew it was a straight line. So it looks something like that. Now, so that's y equals 2 minus x. B, hence, find any solutions to the equation 2 minus x equals 1 on x. So basically, for B, when does 2 minus x equal 1 on x? That's at the point of intersection, which was at the point 1, 1. So therefore, since the equation is only in terms of x, we only want the x coordinate of 1. So the answer is x equals 1. Now for part C, it says on the domain for any real x, for what values of k does x plus 1 over x equal k have one solution, or no solutions, or two solutions? Okay, so this one's a little bit tricky, and we have to look at the graph to do this. First of all, using the previous question, when k was 2, you would get the equation 2 minus x equals 1 on x. If you plus x to both sides, you get 2 equals x plus 1 on x. So therefore, the solution of this equation is when k equals 2. And for that, the solution was x equals 1. And there was only one solution. Therefore, the equation x plus 1 on x equals k has one solution when k is 2. At this point here, which is at 1, 1. Now let's look at another value of k, such as k equals 4. When k is 4, we get the equation x plus 1 on x equals 4. By minusing x to both sides, we get 1 on x equals 4 minus x. So to find the solutions for that equation, we need to look at the points of intersection for y equals 1 on x and y equals 4 minus x. So where would y equals 4 minus x be on this graph? So it would hit at 4, and it would go down to this 4, and you can check that by using your usual graphing techniques. And so I'm just doing a quick sketch to show you. This time there are 2 points of intersection. So in other words, we would actually have 2 solutions to the equation x plus 1 on x equals 4. Basically, when k is bigger than 2, my line is going to look something like this. So when k is bigger than 2, such as 4, it's that green one. If it's k is 3, it's going to hit it there and hit it twice. If k is between 3 and 4, or bigger than 4, or bigger than 2, I'm always going to hit it twice. Similarly, on the other side, if k is negative 3, I'm going to hit it twice there. And like here and here, they're all parallel lines, but they're different values of k. So what that's told me is, because it's symmetrical, when k is bigger than 2 and less than negative 2, we will have 2 solutions to the equation x plus 1 on x equals k. What about when k actually equaled 2? Well, that had one solution when x equals 1. But that also happens when k is negative 2. So when k equals 2 or negative 2, x plus 1 on x equals k would have one solution. To explain that a bit further, I will show you what happens when k is negative 2. So with the equation, if k is negative 2, then it becomes x plus 1 on x equals negative 2. By minusing x to both sides, you get 1 on x equals negative 2 minus x. So let's graph both sides and see what happens. So basically, when k is negative 2, so I want to graph y equals negative 2, negative x. So what would that look like? First of all, some of my graphs disappeared, so let's put that back in. Okay, so negative 2 minus x. Well, when x is 0, y is negative 2. And when y is 0, x would also equal negative 2. So that would be the line going there and intersecting at one point. So in other words, that line there was when k is 2. That line there was when k is negative 2. So when k is 2 and negative 2, we have one solution because they only intersect the graph of y equals 1 on x once. Where do you think no solutions will happen? That's in between here. So that's these lines here, in between the two graphs. That's when k is between, that's when k is 0. When k is 0, y equals negative x is this line here. So that would be no solution because there's no point of intersection with our original 1 on x. When k is 1, it would be this line here. Again, no solution. When k is negative 1, be this line here. And when k is negative 1.8, it would be this line here, but no solution. So therefore, there's no solution when k is between negative 2 and 2. So to finish off, for what values of k does that equation have one solution? That's when k equals plus or minus 2 because there was one intersection. When does it have no solutions? That's when k is between negative 2 and 2 because the line didn't intersect with the curve 1 on x. And when does it have two solutions? When k is bigger than 2 and when k is less than negative 2. Okay, so that was a little bit complicated at the end there. Have a try yourself and let me know if you have any problems. And the exercise to give a go at is exercise 5A. Thank you.